Yeah. Okay. So let me say a few words about Professor Christian Spiering. So you can see in your flyer, we have already shared it. So he's a leading figure in the field of astroparticle physics, and he is one of the pioneers who is responsible for the discovery of these high energy astrophysical neutrino events in big neutrino observatories. Okay, so from the morning you are learning, right, that the goal is to catch those very high energy neutrinos, correct? And they are coming from very far distance, and IceCube has done that job. But when I say IceCube has done the job, you know that there are people behind that, right? And he's one of them. He's the leader, he's one of the leaders, okay, who fulfilled that dream. And now we see those neutrinos. So you can read, we have a brief description about him, but I will not stand between Christian and you. So, Christian, the floor is yours.
Okay, thank you, Sanjeev. And once more, good afternoon to everybody. Let me start with one remark. Of course, it was not me who discovered high-energy neutrinos. The discoveries in this field are typically made by PhD students, by young people, by people like you here in the audience. And so this should be an encouragement for you to go into that direction and to discover the mysteries of the high-energy cosmos. So I named my talk From Cosmic Rays to IceCube, A Voyage Through a Century. What you see here is the building of the IceCube laboratory at the South Pole. And I will come back to that building a little bit later. I named my talk A Voyage Through a Century, and let us make a step back 1 century, even a little bit more, to the year 1912. In August 1912, Victor Hess, he was an Austrian physicist. He took off with his balloon. You see him here still on Earth. And what he wanted to measure is how the ionization changes the farther he gets away from the surface of the Earth. I mean, you have in the Earth, you have radioactive substances, and they emit ionizing radiation. And the expectation was that the higher you go with your balloon, the less is the ionization. But he found the opposite. The higher he goes, from 1 kilometer and higher, the ionization goes up. And there was only one explanation. There is coming something from outer space to the Earth, which ionizes the air. And this something was called cosmic rays, and I will come back to that later. Now, let's stay in the same year, 1912. This with Victor Hess was August. This is January 1912. And the people who you see here, that is the crew of Robert Falcon Scott. He was an explorer, South Pole explorer, and he wanted to be the first at the South Pole. When he arrived at the South Pole, you see him here, he realized that somebody else was earlier there. That was Roald Amundsen from Norway. Roald Amundsen made it back without any losses. All these 5 people died on the way back. And it took until 1956 until the first man was again at the South Pole. This was a year when the Americans started to build their South Pole station directly at the geographical South Pole. And this was the first plane. It was called Que Sera Sera. And it arrived in October, and in February, when the Antarctic winter starts, they left the South Pole, and only a few people stayed at the South Pole. You see here the station, which is under ice. a few meters under ice, because in winter it becomes really, really cold, minus 70 degrees, minus 75 degrees Celsius. And so you want to be a little bit below the ice surface not in order not to freeze too much. So, and then today, if you go to the South Pole, I was the first time at the South Pole in winter 1996. When you go to the South Pole, you first fly to New Zealand. There is a town named Christchurch, and from there you take this plane, which owns the American National Science Foundation, and it brings you after 8 hours to Antarctica. And here you see the McMurdo Station, which is the shore station of practically all Americans' inland station. There you stay 1 day or 2 days, and if weather allows, you go another 1,000 kilometers to the center of the South Pole, where the Americans have the center of Antarctica, where the Americans have the Amundsen Scott Station. And this is how it looked when I have been the first time there. You see on the right-hand side the station with all the smaller buildings, and here cargo baggage, and here is what is called the dome, which is a kind of cupola under which the people live. And this is a dark sector. There are all the astronomical telescopes, which of course you do not want to have them here, because you have here always a bit of light, which is disturbing, and also the radio detectors which are here would not like to be disturbed by the radio traffic which goes from here. So this is the overall situation, and this is the station as it was in the year when I have been the first time there. You see here again this cupola, and under this cupola people live, shielded against wind, shielded against cold by this cupola. So this worked until 2009, but 2006 already this station was taken into operation. The new station, which is elevated, so the snow can flow beyond the station, and you have not so much snow accumulation before the station. Here you see another view from the air. You see it's a huge building. In summer, and summer means Antarctic summer, that means from October to February. In summer you have about 200 people at the South Pole. And in winter it is only 40 people, 35, 40 people. And they stay there and keep the station running and keep the experiments running. So much about the Amundsen Scott Station. Now let's go back to cosmic rays and to the neutrinos from cosmic accelerators, which we want to detect. So let's look once more to cosmic rays. Cosmic rays consist to 99% of protons, light, and heavy nuclei, and only 1% are electrons. And if you look to this graph here on the right-hand side, you see the flux of cosmic rays in dependence on the energy. Here is the energy 10 to the 10, 10 to the 12. This is the energy of the highest particle beam on Earth from the Large Hadron Collider in CERN, which is a little bit higher than 10 to the 12 electron volt. But you see it goes much, much higher. But of course, the flux drops extremely. What you see here, this scala, this is one tick, is 1 order of magnitude. So these are 30 orders of magnitude here. And of course, if you have here 1 particle per square meter and per second, it's here only 1 particle per square kilometer and per year. So you need huge detectors to catch some of these most energetic particles on this edge. And the energies, as I said, are huge. They are 10 million times more than the protons have in the Large Hadron Collider at CERN. And now the question is, how manage nature to accelerate particles to such high energies? So this is one option. This is the remnant of a supernova explosion. It happened 1,000 years ago, in the year 1054. This is called the Crab Nebula. And on the front of this expanding matter, particles can be accelerated. Indeed, they can be accelerated to very high energies, namely to 10,000 times of the Large Hadron Collider. Not 10 million times, but 10,000 times. If you want to go higher, you have to go outside our own galaxy. The supernova remnant is in our own galaxy, but for higher energies, you have to go outside. And there's one preferred object where particles can be accelerated. These are active galaxies. These are objects where you have in the middle, in the center, a super heavy black hole, so millions of solar masses. And this black hole accretes matter. The matter falls into the black hole, and of course, there is released a lot of gravitational energy. And this gravitational energy, which is released, can be transformed to high energy particles, either here in the center or along these jets, which are emitted perpendicularly to the galactic disk. And if you calculate that, indeed, with these objects, you can accelerate particles to energies 10 million times of the LHC energy. So, but we have not identified very clearly these objects as the sources of cosmic rays. Why? That will be explained on the next slide. Firstly, let me tell you how you generate neutrinos from these cosmic rays, from these protons which have been accelerated. So the protons emit, they hit a target that could be dust, that could be photon fields, and then secondary particles are generated. And among these particles, for instance, are pi mesons. And these pi mesons decay in a muon and a muon neutrino. So you have here already one neutrino. The muon itself decays always, also in a positron, that is an antiparticle of the electron, and an electron neutrino and an anti-muon neutrino. So you have per pion, you have two muon-kind neutrinos and one electron neutrinos. And now the point is the following: the cosmic rays are charged, and if they move through cosmic space, they are deflected by the magnetic fields in cosmos. And these magnetic fields are not regularly, they are rather stochastic. And so the particles are accelerated, are deflected in a way which we cannot reconstruct. So they come from this source, and here it looks as if they come from that direction. So they did not lose energy, but they lost their directional information. And for that, you need neutral particles, and there are only two particles which we can use: photons. At high energies, you call them gamma rays, and neutrinos. Gamma rays have the disadvantage that they can be absorbed by matter between the object and us. Neutrinos, of course, they go through everything. Of course, they are hard to detect exactly because they go through everything, but they will not be absorbed, and there will no effect on these neutrinos, neither in direction nor in energy when they arrive at the Earth. So how do we detect high energy neutrinos? Of course, if you speak about solar neutrinos or low energy neutrinos, there are a lot of them, and you can go underground, deep under the Earth, where you are shielded against charged cosmic rays, where is no background, but the detectors underground are large enough to detect, for instance, solar neutrinos. If you want to go to these very high energy neutrinos, they are very few, very, very few. And so you need huge detectors to catch at least some of them. And this is the way how you do it. You arrange a matrix of photomultipliers deep underwater or under ice, as an ice cube. And these photomultipliers have to be in pressure-tight glass spheres, because there is a very high pressure in deep water. And then you look to this kind of reaction. You have a neutrino which comes from below. It has crossed the Earth, and close to the detector, it makes accidentally an interaction, and in this interaction, a muon, a charged brother of the muon neutrino, is generated, and the muon carries with it this light cone, which is called a Cherenkov cone. So Cherenkov light is something which is emitted when a particle moves faster than the speed of light in that medium. So the speed of light in a vacuum is typically normally called c. This is the speed of light. And in a medium with the index of refraction n, the velocity is called v. So it is then smaller than the speed in vacuum. And if a particle, a muon, can keep the speed of light, if this muon is faster than the speed of light in water, then it emits this Cherenkov light. And now you measure the arrival times of the Cherenkov light at the different space points here in this matrix. And from that, you can calculate the direction of the muon, and that means with plus minus 1 degree or plus minus half a degree, also the direction of the muon neutrino. And the energy can be estimated from the total amount of light which the muon emits. So here you see the first dream of such a detector, which was dreamed in 1973. This detector was called DUMANT, Deep Underground Muon and Neutrino Detector. It was supposed to be built close to Hawaii in the Pacific. And the idea was to have more than a cubic kilometer of water with more than 20,000 optical modules. So this was the idea. And then, of course, it became rather clear that this is much too ambitious, and the detector has to be scaled down. And at the end, it was scaled down to something of this size, this green thing here. That was the idea when the funding was approved in 1988, but at the end, nothing did work, and the project was terminated in 1996. So at the same time, the Russians, together with us from Germany, built a detector which was called NT200, Neutrino Telescope with 200 photomultipliers. Look, it is extremely small, this blue thing here. It's only 70 meters high and 40 meters in diameter. It is only a test experiment, but we have detected indeed the first neutrinos with such a kind of detector. The next was the Amanda detector. This was a predecessor of IceCube at the South Pole. Look, this is already significantly larger. And the next have been the Antares detector in the Mediterranean. Same size like Amanda. And today we have indeed a cubic kilometer detector. This is the early dream of DUMANT, and this is our IceCube detector. 1 cubic kilometer, 5,000 optical modules. It was completed in December 2010. And here you see how upward moving muon looks in IceCube. So what you see, all these small points are positions of photomultipliers. And then you have here a muon which goes up, and every optical module, every photomultiplier which is hit is here such a colored sphere. The color gives you arrival time. So red is early and blue is late. And the size of the symbols give you the amplitude, which have been seen by that photomultiplier. So what you see here within a few seconds, in reality lasts only 2 microseconds, 2 millionths of a second. So what do we see there? Which kind of particles do we have in our detector? Most of them are muons, which have been generated here in the atmosphere by cosmic rays, by charged cosmic rays. They hit here the atmosphere, the muon is generated, and it punches, if the energy is high enough, it punches down to the detector, and it can be detected. if it crosses the detector. Then we have, of course, atmospheric neutrinos. They are also generated in cosmic ray interactions. They can, in contrary to muons, neutrinos can cross all the Earth. So a particle, and then they make here close to the detector, they make an interaction, and then you have a muon which crosses the detector. And the difference to this muon is this muon comes from below. And this must be due to a particle which has crossed the Earth. So that must be due to a neutrino. Atmospheric neutrinos are not the only ones. Of course, what we really want to detect are extraterrestrial neutrinos. That are neutrinos which are generated in the cosmic accelerators from where they come, millions or billions of years away from us. They have typically a bit higher energies than the atmospheric neutrinos, so you have a shoulder in the energy spectrum at higher energies. And if they come from a distinct source, you would see an excess of neutrinos in that direction. So there's a background of atmospheric neutrinos, and these neutrinos would appear as an excess in a certain direction. All that will be shown by you later, by Marek Kowalski. So, cosmic neutrinos from cosmic accelerators, they are very, very rare. The flux is 0.001 neutrinos per square centimeter per second. And please keep in mind that of these neutrinos, only millions or even less would make an interaction. These are you need really big detectors to detect them. The neutrinos from cosmic rays, the so-called atmospheric neutrinos, are much more. They are much higher. They have a much higher flux. It's about 1 neutrino per square centimeter per second. They are generated similar to the neutrinos in cosmic accelerators. That means you have here a cosmic ray. It hits the Earth's atmosphere and generates, in this case, pion. The pion decays in a muon neutrino and a muon, and the muon decays in an anti-muon neutrino, an electron neutrino, and a positron. So you have here again two muon kind neutrinos, a muon neutrino and a muon antineutrino, and one electron neutrino. If you look to the spectrum which we measure, it looks like this. Oh, sorry, I first want to show this here. Atmospheric neutrinos have been detected in 1965 at two places, practically at the same time, in the same months. And one of these places was indeed in India. It was a Kola goldfield mine, 2 kilometers deep. And you see here the entrance to the Kola goldfield mine in the 1960s. That have been underground detectors. For atmospheric neutrinos, the fluxes are high enough, so you do not have to go necessarily underwater, but you can stay underground and make a big cavern in which you arrange your detector. So say 10 meters times 10 meters times 10 meters or something like that, not a kilometer. So now I want to show you how that looks like. Is a spectrum of atmospheric neutrinos as it has been measured by different detectors. You see here IceCube, you see here Amanda, you see Super Kamiokande, which is the biggest underground detector which we have today. It is 70 meters high and 60 meters in diameter in Japan, and also some other detectors which I do not want to discuss in detail. So what you see here is in red are the muon neutrinos, and in blue are the electron neutrinos. And the ratio, as I said, is 2 to 1. So what you see here is really 2 to 1, but this ratio becomes bigger and bigger if you go to higher energies. And the reason is the following: if the energy is very high, the muons have no time to decay. And before they decay, they hit the Earth. They are stopped by the Earth, and then they emit only very, very low energy neutrinos if they decay, and these are below the scale of this graph here. What you see here, by the way, is not the flux itself, but it is the flux multiplied with the square of the energy. Otherwise, it would be very, very steep. You could not see any details. And so this is multiplied by E squared. So it is a little bit, you can see really the details there. So now let me come to IceCube. Again, this is a view to the Amundsen-Scott station. And this is IceCube. IceCube consists of 86 strings between 1.5 and 2.5 kilometers. Most of them have a distance between the strings of 125 meters, but some of them, 8 of them, are much closer to each other. And that leads to a lower energy threshold. If the strings are closer, you get much more light. And so the energy, the threshold for the energy is for deep core 10 GeV. For IceCube, it's higher, it's about 100 GeV. And then you have at the top, ice top, which are tanks, which are filled with water. Of course, the water is frozen at the South Pole, so it's ice. And they are used to detect the cosmic rays which hit the Earth, or better to say, the ice surface at the South Pole. So this is the central part of IceCube. Here you see a photomultiplier. So if a photon hits the photomultiplier here at the surface of the photomultiplier, an electron is released. The electron is accelerated to this place, and there is a construction which amplifies one electron to 10 to the 7 electrons. So at the end here, you have that's why it is called photomultiplier. At the end here, you have 10 to the 7 electrons, which is already a measurable current. So this is I will not discuss the other things here. A lot of calibration things, and here's a Mühlmetall against the magnetic field of the Earth, etc., etc. This is how it looks in reality. Quite a lot of electronics. And here you see how these things behave over the past 15 years. So this is a survival fraction of all these optical modules. You know, these are very delicate electronic devices, and you would expect that after 15 years, 10% or 20% have been failed, but no, after 15 years, still 98%, 98.5% are operating, and we hope that will continue over the next 2 decades. So now, how is IceCube built? It is not built by drilling holes in the ice, but by melting holes into the ice. You have here a heating factory, which brings the water to 80 degrees. And then this 80 degrees hot water is pumped here and pressed through a nozzle to the ice. So for that, we need 5 megawatt power and 16 cubic meter kerosene per 1 hole. So that's quite a lot, and all that has to be transported by planes to the airport, to the South Pole. Now, here you see again the principle, and this is this instrument for drilling the holes to the ice. So at the end of this cylinder here, there is this nozzle which presses the hot water to the ice and melts it down. This here is used to keep the sink always vertical and in a distance to the walls of the ice hole. So you see it here once more. Here at the bottom there is this nozzle which flashes the 80 degrees hot water to the ice. And here you see how it goes down. So these things here keep the right distance to the wall. So now I have to say this works only if you are deeper than 40, 50 meters. If you are at the surface, you must remember that the ice is made from snow, which has been fallen. It's not like in a river where the ice freezes, but you have snow, and the snow is, of course, very light, and the water can diffuse into the snow. This is called firn ice. And then only step by step, year after year, the ice becomes more compact, and it lets not water diffuse into the ice. So for the first 30, 40 meters, you have to take this here, which is practically a copper thing, which is very hot and which really does not need any water. It just emits high heat, and then you go with that down to 40 meters, and then the ice melting thing starts. So let me show you once more here this video. So you have first this heater, which does not need any water, first 40 meters. And now the water comes, 80 degrees hot water, and melts the ice down, 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 down. That takes about 2 days. And after 2 days, you are at a depth of 2.5 kilometers. And then the thing is done. And then you can, oops, in a moment. So, and then you can let down your optical modules into these ice holes. So the last string of IceCube was completed in 2010 at the December 18, and here you see the happy crew of those people. Let me come back once more to this building. All the cables which come down from the strings, they go here to these towers. Then they are thrown through these towers. They go here into the building. And in the building, you have all our surface electronics, which go then to, which gives the signals into a computer farm. The computer farm makes immediately the reconstruction of the events. So it calculates the direction, the energy, etc., etc. And then all this is sent by satellite to the northern hemisphere. So, you know these two guys? You know them, presumably. That are Ernie and Bert. They are comic figures from a broadcast for children. And they are very similar to these two guys. These are Ernie and Bert in IceCube. These are two events. So let me say first, when the detector was completed, 2010, we were not sure whether we would detect cosmic neutrinos at all, because you can calculate the flux of solar neutrinos with an accuracy of 1 or 2%. But the flux of these cosmic accelerators at very, very high energies is not so good known. It's known to an order of magnitude, not more, maybe even worse. And so it could easily have been that the detector would be a little bit too small, and we would have spent $270 million and would not have detected anything. And indeed, in the first 2 years, it looked like that. But then in 2012, these two events have been detected by two Japanese PhD students. And their energy was so high that it was rather clear they presumably are not from the atmosphere. They must be cosmic neutrinos from far away. The probability that they are from the atmosphere was less than 1%. So less than 1% is not yet a proof. But then 1 year later, we had selected a lot of such events. And what you see here is the number of events, and here the energy in giga-electron volt. And this is what we have measured. These crosses here, these are error bars. So sometimes it's only a very few events, or here no event. And then you have what our simulation calculations gave us. So in blue, you see atmospheric muons. That are muons which come from the top. They move down, but they have been misreconstructed, and we think they come from down and move up. So this is in background which was not fully excluded, and this is what we expect from our Monte Carlo simulations, that it looks like that. Then you have here what you expect from atmospheric neutrinos. And then you have here the rest, which would explain our data. And this rest in yellow, that are the cosmic neutrinos. And for this, the probability that this excess is accidentally was already less than 100,000. So that was already practically a discovery, and for that discovery, we were awarded a prize, namely the breakthrough of the year 2013 by the journal Physics World. And Francis Halsen, which is really the spiritus rector, the boss of IceCube. So I was for some time, I was a spokesperson, and of course I have a long history, but the real father of IceCube is Francis Halsen from the University of Wisconsin, where Zhang Yip has also been working, and he has obtained a lot of prizes, not yet the Nobel Prize, but
So,
maybe.
Christian,
Yeah.
May I interrupt you? Like, the connection was broken for the last 1 minute.
Okay.
So we are trying to restart. Just 1 minute.
Do you hear me now?
Yeah, Krishna, we hear him now clearly. No, just wait.
Do you hear me now?
Yeah, I hear with my mobile, but let me just figure out. So what happened here?
Okay, so I will repeat.
Yeah.
I will repeat the last minute.
Tell him that.
Zhang Yip, I will repeat the last minute. Is that okay?
Yes, sir. Yes.
Okay, so what I said in the last minute is that indeed in 2013 we had the proof that this excess is definitely due to cosmic neutrinos. So we have discovered cosmic neutrinos. Marek will tell in the next talk more detail about that. So wait with your questions until Marek makes his talk. But what I wanted to say about this picture, it shows again the IceCube laboratory, and this, what I mentioned, is the prize from Physics World, which is a new physics journal, and they gave us a breakthrough prize of the year 2013 for discovering cosmic neutrinos. And what I then said, this was not the last prize for IceCube, but the prizes which IceCube got have been mostly given to one person, which is Francis Halsen from the University of Wisconsin, where Zhang Yip has been working. He is the real father of IceCube. I am happy to be a leading member of IceCube, have been a leading member. I am now 77 years old. I'm retired, but I'm happy to be one of the party. But he is really the father of the experiment. So that was in principle all what I wanted to say about the detector, and about the physics results. It will be Marek Kowalski who will talk about that. Marek was a PhD student, a diploma student and a PhD student in my group and then he went to the United States and worked in cosmology, where he also has a considerable record of results. And then he came back to Germany, was professor in Bonn, and then came to DESY, where he made his PhD. And he then took, so to say, my position, and is now the leader of the group and also professor at the Humboldt University in Berlin. So that was all from me.
So let us thank Professor Christian Spiering. So thank you, Christian. Your talk was really good, and this is what we basically anticipated, and it was very lucid, and I'm sure the students here with their prior knowledge they could appreciate. So now before we start the next talk by Marek, is it okay if we take some questions, Christian?
It's okay, but keep in mind that I have a hearing problems. So
Okay.
maybe I have to ask twice to understand the question.
Okay, okay, we will try our best. Yeah. So now, students, if you have questions, we can discuss them. So who will come first? You have any? So raise your hands, and then we'll take one by one. So you want to have questions? Yes. Can you come? Yeah. So just stand up and introduce loudly and ask your question.
My name is Diksha Pradeshini Patra, and I have a question regarding the Cherenkov radiation. It emits a light, but
Sorry, I do not. Hello, do you hear me? Hello, hello?
Christian, I hear you, but I don't know if the others are. I'm not hearing the students either.
Okay.
Christian.
So now I hear you again. Could you repeat the question?
So we have a student here, and she's asking that we see the Cherenkov radiation, right? Now, can you repeat your question?
my question is, why do we see a light when it's faster than light, and why is the light blue?
So, why we see a light when it is faster than the speed of light, and why it is blue color?
Oh, you know, that of course at the end it has a spectrum which goes with 1 over wavelength squared. So it peaks at low wavelengths. Actually, the maximum of the Cherenkov radiation is in the ultraviolet. And of course, we cannot detect with our photomultipliers ultraviolet. And that is also not necessary because the transparency of water and of ice in the ultraviolet, in particular of water, is extremely small. So if you go below, say, 350 nanometers, the absorption length of light is a few meters. So what we need, of course, is tens or hundreds of meters absorption length. So that is so it's not only blue, but at ultraviolet it's practically zero because it goes as 1 over wavelength squared. So now, if it comes to a generation mechanism, it becomes a little bit more difficult to explain. It is at the end is a kind of it is a kind of I don't find the right word, polarization of the dipoles. You know, the atoms which are passed there at the end, kind of dipoles. You can, and the molecules, you can polarize them a bit if an electrical charge passes along these dipoles, and then they fly back to their original orientation. And this is the time when the Cherenkov light is emitted. So that is all with what can explained in easy words. If I would try now to go into deeper details, I'm not sure whether I could do that without a table and 10 minutes at least.
So I believe your question was why the light is blue.
And why it produces the light when it's faster than light.
Yeah,
Yeah.
you know, this is what I said. If you calculate these, so if you calculate if you make the theory for Cherenkov light, which by the way was not known when it was discovered, and only some months or years later, other people made the explanation. They got the Nobel Prize for it, so it was not trivial to make that explanation. What do I want to say? Yeah, and that is a rather complicated explanation. If you make it as a formula, I try to make it in words, but these words do not explain why it goes so up in the ultraviolet. For that, you have to have a theory, and that I cannot explain here in a few words at a computer. Marek, can you?
Yeah, so your questions are well taken, and I believe you got some hint that every light has a wavelength, right? Basically. So there are many wavelengths involved, but the dominant wavelength, which gives like this blue light, basically. And
Yeah, that's it. I mean, it goes like 1 over wavelength squared. So, and the lowest wavelengths which we can see with our eyes is blue. And that's why it is always shown like blue. Of course, it has also some green components, but these higher wavelengths have a lower contribution to Cherenkov light.
so every wavelength will appear as a different color, but the wavelength of our range will give you blue color. Okay, so that is one part of your question. And another is that why this Cherenkov light? So it needs little bit of theory, and I believe that if you stay little bit longer, we will give you some more light towards that. Okay, is that okay? Yeah, but your question is highly appreciated. It's a much deeper level question, but I'm happy you asked this question. So now let's move on to some other question. Be loud so that he can hear you. Yeah, can you introduce yourself?
Guten Tag, I'm Amrit Sarangi. So my question is, how do we know a particle detected is actually because of a neutrino?
Once more.
My question is,
Then-
how do we
yeah.
know that a particle detected is because of a neutrino? The particles can be independent of their own also.
Can
So
we-
the question is, how do you know that the particle that you have detected is neutrino, not any other thing?
Yeah, okay. Sorry. There are several ways to make this distinction. One way is that you look only for particles which move upward. So because these particles, so muons, which cross the detector, and they come from below. And then, of course, you know, these muons must have been generated in an interaction of a particle which has crossed the Earth. And crossing the Earth is only possible for neutrinos. All charged particles, also other particles, charged or non-charged, photons, for instance, would be absorbed after a few meters, after a few kilometers. No particle, only the neutrino can cross the Earth. So this is one way to distinguish them. The other way is you can also look upward in principle, but then you have to make sure that nothing comes from the top, and only in the middle of the detector something happens. So there is no charged particle coming from the top, and then only in the middle of the detector, inside the detector, something appears. So the primary particle has not been seen. And the only particle which would not be seen is a neutrino. Photons would not go into that depth. And that is the other way to distinguish these things. Ernie and Bert, these two particles which I have shown to you, are similar to that, not exactly like that, but it was also clear that there is nothing coming from above, and there is something in the detector which happened, and there was no charged particle which could be the source of this event.
Thank you.
So you got the answer. So if something coming from the below, basically, then only neutrinos can pass through the earth, come to your detector, give you signature. Any other muons? Right, correct. But this is a very good question, and we can clarify it more during the break and all. Okay. So let's move on to some other questions. Yeah. Can you come here, please? Because just allow her to come close to the microphone and speak loudly, introduce yourself, and ask your question.
Hello, myself is Vanchika Ravketa. So my question is that what's the current status of neutrino mass based on their order, and what implications would resolving this hierarchy have?
So Christian, this is a physics question. So he's talking about a neutrino mass, right?
It's based on their orders.
So what orders you assign the neutrinos in their masses, and what is the current status? So he's talking about neutrino mass ordering problem, basically.
You know, actually, this is a question which is also important for us in several respects. First, the neutrinos which come from far away, they have typically a ratio 2 muon neutrinos per 1 electron neutrinos. That's how they are generated in the sources. Now, on the way to the Earth, they oscillate, and oscillation is a thing which is only possible if the neutrinos have a mass. They oscillate from one type to the other. And what arrives at the Earth is not 2 to 1, that means 2 muon neutrinos, 1 electron neutrino, but 1 to 1 to 1. We have 3 neutrinos, and they arrive in equal proportions. 1 electron neutrino, 1 muon neutrino, 1 tau neutrino. So that's something we have to consider if we derive physics result for high energy neutrinos. Now, I explained to you that we have there also a detector, top detector, which is called deep core. And that goes to much lower energies, to 10 GeV. That is the energy threshold of deep core. And at these energies, already oscillations of neutrinos which have been generated on the other side of the Earth, they cross the full Earth, and on that way they also oscillate. So if we look down, we see only half at low energies, at very low energies, we see only half of the muon neutrinos which we would expect, which we measure from top. And this is a clear sign that there are oscillations. That is an observation which has been made already in the 90s by a Japanese physicist called Takaaki Kajima, and he got the Nobel Prize for that in 2015. So we see that effect also, and this effect of neutrino oscillations, this effect is only possible if the neutrino has a mass. We do not know the exact value of the mass, but we know the mass differences between the 3 neutrino mass states. And that is something which we can also measure in IceCube. Maybe, Marek, do you have something about that in your talk? Anyway, we see that and we can measure that, but the real, we know, as I said, we know only the mass differences between the mass states. We do not yet know the mass itself. We know rather definitely that the mass is smaller than half an electron volt, that we know from an experiment here in Germany called Katrin, and we guess that it is even smaller than 0.2 electron volt. That is what the cosmologists say us. But more we cannot say about the absolute mass. We know only the mass differences, and that we see indeed in our detector and can measure in our detector.
So your question is very involved, but you understood that we know the absolute mass, from an experiment called Catherine, and it is, we discussed in the morning, almost 6 orders of magnitude smaller than the electron mass. But your questions were how the masses are ordered. So we know the difference between the masses because there are 3 neutrinos. So there are 3 mass states, 1, 2, and 3. So we know that 2 is above than 1, but we don't know the third part guy, whether it is below 1 or above the 2. Okay, and that issue, there is a part of the IceCube detector called deep code, and we are sensitive to that. But I think we can take this question later. But this is a very good question, and maybe next speaker may shed light on that. Okay, let's wait. Let's move to other questions. Yeah, come here, come close. So you can introduce and you can ask your question. Please the mic.
Good afternoon, sir. I'm Anushka Malik. And today, the entire day, whatever we've learned, we've been hearing about anti-neutrinos. And after some research, I got to know that it's also generated during beta decay. So does it have any significance in the entire process?
Sanjeev, could you please repeat the questions for me?
So he is asking that today she got to know about anti-neutrinos. So does it have any implications in the entire process? Because mostly you said neutrinos, but what about anti-neutrinos? This is what she's asking.
Yeah, practically every particle, with some particles are their own antiparticles, for instance, a photon. But neutrinos, after all what we know, are not their own antiparticles. They have all the other particles, they have an antiparticle, and so they are typically, so for instance, a positron is generated together with an antineutrino. An electron is generated together with a neutrino, so that there is something which we call, Sanjeev, I don't know whether this goes too deep, but there's something which we call the lepton number, and the lepton number must be conserved.
So they are familiar with beta plus and beta minus decay. So
yeah, okay. So you see that in beta decay, where you have a neutron decaying into a proton, an electron, and anti-electron neutrino. So the electron and the anti-electron neutrino, the electron has lepton number 1 and the anti-neutrino lepton number -1. So the sum of it are 0, as the lepton number is on the left-hand side, namely the lepton number of the neutrino, which is also 0. So then, of course, these particles, okay, I give you some examples. The solar neutrinos, which have been detected, I do not know whether you talked about that already. These are really neutrinos, while in beta decay, you generate, or in a nuclear reactor, that's where the neutrinos have been detected in 1956. In nuclear reactors, in the beta decays in nuclear reactors, you generate anti-neutrinos. So they are that are really distinct particles.
So you understood, like these are 2 different particles, but as far as IceCube is concerned, like we don't have.
Sorry. Yeah. What IceCube is concerned, a really good question. So we have a muon neutrino and we have an anti-muon neutrino. They generate a positive or a negative muon. And since we cannot distinguish between different charges, we cannot say whether it is from an antineutrino or from a neutrino. So we cannot distinguish between charges, and that means we can also not distinguish between antineutrinos and neutrinos.
So in the exercise, you saw the long tracks. Those are muon tracks. But muon can have antiparticle, anti-muon, right? Mu minus or mu plus. So from that track, it is difficult to say that whether it is mu minus, which is generated by a neutrino, muon neutrino, or it is mu plus, which is generated by a muon antineutrino. Right now in our detector, we don't have that provision, but I can tell you that we have detected antineutrino for sure, because we have a glasso resonance event that we can discuss later, but that event only happens for antineutrino. Okay, but event by event basis, I can't say that this is neutrino, this is antineutrino. For that, you need something else. But this is a really good question. Let's move on. So we have other questions.
Sanjeev, can I interrupt here? I'm unfortunately constrained by I need to by the time.
Yeah, we can stop the question answer and we can start your talk. Yeah.
Okay.
Yeah.
I think
great.
that would be better. Thank you, because maybe you can continue. I don't know if in particular if Christian can stay
Sure.
for after the talk, because I need to leave, I think, at 12 my time. So by the end of the hour.
Just give me a minute. Let me introduce you and then we can start your talk. Yeah. So let's thank Professor Christian again for his talk. So after learning about the IceCube detector, we have now another speaker from DESY, and you can see in the Zoom Professor Marek Kowalski, and already Professor Christian Spiering introduced him, right? So his contributions are noteworthy in astroparticle physics, and you have seen in the flyer the details are written. His major contributions are mentioned there. Since he is in hurry, so we would like to request Professor Marek, if you can kindly share your slides, and students are excited to learn from you.
Okay. Let me see. So, do you see this?
Yes.
And do you see it moving? Do you see the blue screen?
Yes.
Okay, good. Well, okay. So, yeah, apologies for having to leave quickly. I'm also not today I don't feel so good. So if I'm, it's I wanted to give this class, but I'm going to go to the doctor afterwards. But it's I did want to give the class because I think it's a great opportunity to talk to you in India. And I think it's also fantastic to see your curiosity and your interest in the subject of our research. So I'm going to talk. So Christian has talked about how to detect neutrinos with IceCube today, and now I want to talk about both the science, the physics, and as well as some of the recent results. And I will introduce with the sort of the motivation for neutrino astronomy. So I really start with sort of the basic physics. And what we are doing is we are trying to push the energy frontier in astronomy. And what do we mean with energy frontier? We mean essentially the energy of the messenger particle. So you've been talking about synchrotron radiation. No, sorry, you've been talking about Cherenkov radiation. Christian mentioned UV photons. That when you say it's a photon, a UV, a part of the spectrum, or an optical part of the optical or the visual spectrum, that refers to the wavelength. And the wavelength tells you about the energy. And what I want to really tell you about now are the different energy scales that we use to observe the cosmos with. And then you will understand and maybe appreciate the energy that we are trying to, the energy scales that we are exploring through neutrinos. So if you, in a sense, the lowest amount of energy in photons, that's what we call the radio. And not very far from radio is the microwave radiation. So in this case, a photon, the carrier of the electromagnetic force, has a wavelength of maybe a millimeter. And that corresponds, and that's the units we physicists use corresponds to 10 to the minus 4 electron volts. So a 10,000th of an electron volt. I will be using that unit electron volt. You could also translate it into joule or calories. It would be all the same. It's just a transformation. What it refers to is the energy stored in one photon. Okay, so you observe the cosmos with photons of the energy 10 to the minus 4 electron volts, or 1 millimeter in wavelength. You need fairly, large dishes for this, but they don't need to be very precise because the angular resolution is not so great anyway at this wavelength. And so what you're seeing is actually the picture which I'm showing here. It's the cosmic microwave background. It's the first radiation from the cosmos. It tells us essentially about it's about the universe 380,000 years after the Big Bang. And so essentially, initially the universe was very opaque to radiation. You had the Big Bang, you had a very dense environment, photons scattered off each other, of material. They didn't get very far. Eventually, the universe expanded, and then photons were able to escape, and that's the picture you're seeing. Now, I'm not going to speak about the, what you're seeing in this picture. I just want to show it to you. If you could give a full talk about this image, but that would be a talk on cosmology. It would not be about the highest energies in the universe. Let's jump to the next wavelength, and I chose the 1 electron volt. Now, 1 electron volt, you might have not guessed, but that's actually that's the energy scale of the visual sky, the optical sky that you can see, with your own eyes. You might not see the picture that I'm showing here because this is already the full sky, projected onto a map. And of course, wherever you are, you're never going to see the full sky. You maybe can see a quarter of the sky. But if you are in a dark location, in particular, I think in India, you should be able to see the Milky Way. And so, and what you're seeing here is, of course, what you are familiar with. You see many stars. You can't resolve the stars individually so well on this graph, but what you're seeing is the Milky Way band, which is sort of the horizontal band. So you're also seeing something interesting if you look closer at this. It's you're seeing these dark patches in the middle. That's weird, right? Because in the Milky Way band, you would expect to have extra many stars. Well, you have, but much of the radiation from the stars is being absorbed by dust in the galactic disk, in the disk of the Milky Way. And so there's lots of radiation, but the radiation is being absorbed again. And when the absorption is very heavy due to dust, then you're seeing those black patches. All right, so you're already, we are getting familiar with the limitations of electromagnetic radiation. It carries enormous amounts of information, but it can also be absorbed easily. Now, let's jump in energy one more time. Look at the number at the bottom. So right now we had 1 electron volt per photon. Let's see where we are now. Oh, 10 to the 9 electron volt. That corresponds to 1 billion electron volts. So the wavelength of the photons now is 10 to the minus 15 meters. So it's it's a 1 with 15 zeros, and then divide this number, take the inverse, and then that's the wavelength. Okay, so what are we seeing now? We are seeing patches, bright patches away from the galactic plane, and you're seeing, of course, the galactic plane itself light up very nicely. It seems more narrow. It seems sharper, and you don't see the dust absorption anymore. And that's maybe not a surprise because these high energy gamma rays, they punch through the dust. They cannot be absorbed by the dust so easily. I mean, eventually they can be absorbed, but not by the amount of dust that we see that we have in our Milky Way. But you're also seeing, as you're moving away from the galactic plane, you're seeing, dots. And these dots are not stars. Unlike in the previous graph of the optical sky, here they are actually galaxies, so-called blazars mostly, where you have an active galaxy, which means a supermassive black hole that is sort of accreting matter. I'll talk about what this means, and emitting it in forms of jets. So we will meet those blazars later on during the talk. I just want to already point this out here. Okay, so we had a 1 GeV, 10 to the 9 electron volts. Let's move, let's be brave and move to even higher energies, 10 to the 15 electron volts. So we are now at, 1,000,000 times more energy than in the previous image. Unfortunately, I cannot report a single photon that was detected at these energies. And so that's the end essentially of electromagnetic, that's of astronomy with photons. Why is this? Why are we limited? We are not limited by the fact that those photons are not produced. We are pretty certain that you will even have photons at 10 to the 15 electron volts. Instead, we are limited by, oh wait, 1 second, I need to, what's going on here? Okay, sorry. We are limited by the fact that those photons, even if they're produced, they cannot make it to the Earth. They're being absorbed by the radiation that I have introduced to you at the beginning. The universe is full of cosmic microwave background photons. We observe them. And photons can scatter off photons. It's surprising that light can scatter off light. But only if you're not very familiar with the physics. Once you understand, and you think of these as photons as particles, you're not so surprised that they scatter off each other. And in particular, if the energy of two photons that interact approaches the energy of the rest mass of two electrons, you can create E plus and E minus. So positrons and electrons essentially out of the vacuum. So the two photons, in a sense, annihilate, and what comes out is an E plus and an E minus, so an electron and a positron, and the high energy photon is then gone. So as a result, at high energies, where photons are being absorbed, and there's not much you can do about it. So they're not available anymore to astronomers, and you cannot learn about the most energetic sources using photons. Okay. So if you now sort of do this in a more systematic way, you can ask, as a function of the energy that we want to study the universe of an individual particle, how far can I look into the cosmos? How deep can I look into the cosmos? That's shown here in this graph. So it's about, how deep can I see sources in the universe, ranging all the way from radio, the longest wavelength, to the highest wavelength, the smallest wavelength, gamma rays that I mentioned. And you're seeing in black here an area of the universe that we cannot observe with photons because the photons are being absorbed. And it's not a small area, right? It's about a quarter of the full spectrum that is unobservable with photons. And this is exactly where we neutrino astronomers want to shed light on. So this is the part of the universe that we want to actually now learn about. How do we know that there is something to even observe? Well, we know because the highest energy particles ever observed, they're not photons, but they are cosmic ray particles, have energies of 10 to the 20 electron volts. That's another 5 orders of magnitude higher than the 10 to the 15 that I have shown you. Now, we know this because these particles, they interact with the atmosphere and they create these gigantic air showers. The background which you are seeing here is our city, Berlin, where both Christian and myself live in. And so, these air showers, they start maybe 20 kilometers up above the ground, and then they develop and will produce massive amounts of particles. And these particles we can then detect either through detectors on the ground or through imaging techniques. So we know these particles exist. We just don't know actually where they come from. Now, I want to give you a little bit of an illustration, what these energies mean. So I spoke about 10 to the minus 4 electron volts. That's a microwave, and I went all the way up to 10 to the 20 electron. So that's a lot of, many, many zeros. So that's actually 24 zeros that you need to add in order to go from the lowest energies to the highest energy. I want to put this into context of what we can reach on Earth. And so for this, I'm taking you to CERN, to the LHC in Geneva, so Switzerland. So now we are looking at an accelerator, a man-made accelerator in Switzerland. It's 27 kilometers long. It's called the Large Hadron Collider. And the maximum energy you can produce is limited by the magnetic fields that are, that keep those particles, in this case it's protons, on track, so that they, a particle wants to move straight. If you want to make it its trajectory bend, you need to apply force, a magnetic force, and the magnetic force is produced by magnets, and these magnets have a certain limiting field strength. Is essentially the a few Teslas, and beyond that we cannot create stronger magnetic fields. And so if you want to accelerate to higher energies, you would have to either increase the radius or the magnetic field, and both is difficult. So you can use, if you know the radius, if you know the magnetic fields, you can stick it into the equation that I show at the top, and then you can get the maximum energy achievable. And for the Large Hadron Collider, it's 7 times 10 to the 12 electron volts. Now, that's still, a million times less than what we are observing from the cosmos. Okay, you can say, I understand now how to accelerate particles. I do it like the LHC, and you've seen the equation. It's just the product of magnetic field times radius. I can't increase the magnetic field, but I increase the radius. And let's build the largest accelerator that will fit on Earth. And let's just, in our imagination, put now the accelerator, the magnetic field structure around the Earth. Don't worry about whether that's possible or not. Just let's imagine it's, we have this kind of accelerator. What kind of energy would we achieve? Well, we would only increase, the energy by a factor of 1,000. So we would still be missing significant energy. So unfortunately, this is not an accelerator that is powerful enough to explain or to produce the cosmic rays that we are observing. All right, let's be even more brave. Yeah, let's now imagine we built an accelerator around our sun. So, think of it as, you have some kind of accelerator technology, and you're spooling it off while the Earth is rotating around the sun. And you're building the largest conceivable accelerator by, putting it in orbit around the sun. Now, technically, that will be not possible. We don't have to actually think about it too hard. But it's still fun to actually think how much more energy can you produce. And now you actually arrive at 10 to the 7 times the LHC, the Large Hadron Collider energy. And that's essentially where we are. That's the particles that we are observing from cosmos. Now, what are those accelerators that are producing those particles that we are observing? Well, certainly they're not the accelerator that I've just drawn you. I mean, it's certainly not, going to look like the one I've shown you, but I will spend the next few sort of minutes telling you what we are seeing and how we are thinking about these objects. Okay, but before I go down this road, I just want to explain the role of neutrinos, and I know Christian has done this already, but I'll be, I don't think it hurts to see it again. So I've already introduced to you the problem with electromagnetic radiation. It's being absorbed by the cosmos itself, by dust, but also by background radiation. Now, I've mentioned cosmic rays, protons, for instance, and they reach to the highest energies, yet we don't know where they come from, and we don't know because they are actually being deflected by magnetic fields. So if these particles, yes, we can see them on Earth, but if they arrive at Earth, we don't know where they come from because their direction has been scrambled by magnetic fields. So we don't know where they come from. Neutrinos, on the other hand, they don't have this problem. Neutrinos just go straight, so they are not deflected by magnetic fields, and they can tell us essentially about the highest energies. Okay, so Christian has introduced to you how to detect those neutrinos. I will not spend any time talking about the detection anymore. I want to now just talk about the sources and what we are learning. So let's think about what kind of sources could there be. If you just use what we know about our own galaxy, there are only a certain amount of candidates. For instance, supernova remnants. So that's the leftover of a supernova. So a supernova is when a star explodes at the end of its life. It cannot sustain its own radiation pressure anymore. It collapses. And it's not collapsing to a point, but instead it's collapsing to some, limited physical object, perhaps a neutron star, and then it explodes, and it's what we call a supernova, a core-collapse supernova, and that can then lead to a supernova remnant. You have other objects like microquasars or pulsars, and all of them, in a sense, are can produce high-energy particles. I will explain how, but there's a certain limited energy, and again, you can use the equation that I've shown you, which is the product of magnetic field B and radius r, and you can estimate what is the maximum energy that you can produce in galactic sources, and it's about 10 to the 15 electron volts. So it's not enough to explain the highest energy that we observe, which is 10 to the 20 electron volts. Now, luckily, there are other candidates. You can't find them in our own galaxy, but once you go to, out of our galaxy, the universe becomes pretty wild. So the things we are seeing are, for instance, active galaxies. An active galaxy, I mentioned this already, is not just a galaxy like our own. It's actually a galaxy that is accreting matter. So the two ingredients you need to have an active galaxy is a supermassive black hole in the center. Now, it turns out that that's actually true for most galaxies. You almost always have a supermassive black hole in the center. But if you want to actually activate it, you also need to feed the black hole. You have to feed it with matter. And when that matter around the black hole is available, then you speak of active galaxies. And these are shining very bright in all sorts of wavelengths. Okay, so this is, for instance, an illustration that we have created. So what you're seeing here is the supermassive black hole in the center, but you're also seeing the accreting material. It's arranged in a disk. I'm not going to explain why, but think of it as a disk around Saturn. When planets form, the debris, in a sense, finds itself in a disk. So disks are pretty natural, and it spirals around the black hole. Now, I want to explain now in a few words, and you can ask me questions later, how to generate energy from a black hole. First of all, I think the most important thing there are a few important things to recognize. First of all, when matter falls onto a black hole, the matter doesn't just fall into it quietly. Instead, only half of the energy that actually is being released is actually is taken into the black hole. The other half is radiated away. That's not it's not a very firm statement. It's I could explain to you why it's a good it's a good approximation, but it's not an exact ratio. It depends on many things. But it's something to remember. If you throw something onto a black hole, half of the energy that is being released through the gravitational forces will escape in one form or another. Let's ask how much energy we are releasing in the first place. How much do we, when we throw things onto a black hole? So for this, I'm introducing the radius of a black hole. And now there are different people talk of gravitational radius or Schwarzschild radius. I will talk about the Schwarzschild radius here, and they are very closely related. And this is essentially the radius from which no light or matter can escape a black hole. Yeah, so that characterizes a black hole. It's the radius itself is just proportional to the mass of black hole times 2 times the gravitational constant divided by the speed of light squared. It's that simple. If you want to escape a black hole and you happen to start at the Schwarzschild radius, you are not going to make it. Whatever energy, whatever particle you are, whether you're a photon, if you're a human being, it's even worse, I think. For many reasons, I'm not, but that you have bad luck. In any case, you're not going to escape the black hole if you are at the Schwarzschild radius or closer to a black hole. Okay, so this is the length scale. Maybe just as a reference, if you're thinking of a black hole that has the mass of our own sun, the radius would be 3 kilometers. So if you take the mass of the sun and compress it to a sphere that is just 3 kilometers in radius, then you have a black hole of a solar mass. All right, and now I want to combine it with an equation that you know, namely the potential energy of, I hope you know, actually I don't quite know whether you have learned this in high school, I hope you did, but if you know, the potential energy from a gravitational potential, it will fall like 1 over the radius, okay? And so the closer you go to approach the center of the potential, the more energy you're transferring from potential energy to kinetic energy, okay? And so think of the test mass as this blue dot here, which you see on the top of the graph, and it's falling into the black hole. Now, you don't, there's no point in going closer to than the Schwarzschild radius, which is, you know, I have just made this graph for a stellar black hole mass, so 3 kilometers radius correspond to the Schwarzschild radius. It's also symbolized by the black big circle here, yeah? So there's no point in going closer to black hole than the Schwarzschild radius because you're not going to observe anything coming out of it anyway. So let's just worry about the blue dot until it hits the Schwarzschild radius. So it rolls down this potential, and by the time it actually intersects the Schwarzschild radius, it will have gained kinetic energy, okay? How much? You just punch it into the equation. You insert for the radius the Schwarzschild radius, which is 3 kilometers. You take as a black hole mass. You know, it doesn't quite matter what you take because the black hole mass itself, it actually cancels. All that remains is you know, a very simple equation. G also cancels. So you get as a, you know, the kinetic energy that is being released is just 1/2 times the mass of the particles times c squared. Okay, very simple equation. At least to a physicist, it's about as simple as it gets. For you, it might be very, you know, you might be seeing it for the first time, probably you will, and it will look very awkward that you can come up with such a simple equation. Maybe you don't even quite understand it, which is fine. It's about, you know, but this is what physics is about. You want to compute things and understand the sort of physical limitations. Now, what does it mean? You can, you know, you're taking a particle, throw it at a black hole, and you're releasing, essentially it accelerates and it will have an energy of 1/2 times mc squared. Now, at this point, you have to remember, and maybe you can't remember because you haven't learned about it, but Albert Einstein actually wrote down what the mass, what's the energy is that is associated with mass. And there's a very famous equation, and that is that the energy is equal to the mass, the rest mass energy is equal to the mass to the power of c squared. Okay, so what we're learning from this black hole physics is that when you throw things into a black hole, you're releasing half of the rest mass energy. Half of the energy stored in the mass. And that is enormous. To a physicist, that is pretty fantastic, because if you compare it with nuclear processes, for instance, a nuclear reactor, you can only release, you know, 1 or 2% of its rest mass, so a much smaller fraction. Here you're releasing 50%. So you have an incredible source of energy here when you throw things onto black holes. All right, you know, that's one thing to know. The next thing is astrophysics. How, you know, you don't just throw things onto a black hole. Actually, it's more complicated. I can't go into the details, but I can just say, you know, when you will have create shocks. Shocks are, you know, are always created when you have matter, you know, traveling at different speeds and interacting with each other. And when you have shocks, you will be able to translate sort of energy and accelerate individual particles. So bulk kinetic energy is being translated into energy of individual particles. And at this point, I don't want to say exactly how you accelerate particles for multiple reasons. First of all, it's complicated. And second, we don't quite know. It's really research we are still undergoing. But there are ideas how to take this gigantic energy resource, and translate it into a very high energy particles, so accelerate particles. All right, I want to now talk about you know, what we are learning, and I try to be quick here. Let me skip over this. Christian has mentioned high energy neutrinos, particles. So we are you know, we are actually looking for the sources of these high energy neutrinos. And what you're seeing here is one high energy neutrino as it goes through IceCube. And this is an interesting neutrino because we saw this neutrino and we actually understood pretty quickly that it's actually connected. It's to a so-called blazar. So it's an active galaxy that is producing a jet, and we are looking right into the jet. And we were able to pinpoint the jet because the neutrino was, we were pinpointing the source because the neutrino was pointing right at this object. And so when we reconstructed the direction, it aligned with that very object. And that object at that time was also very interesting. It was flaring in gamma rays. And so just to visualize this, this is not a movie of a real thing, but this is how we understand it. And that's our animation of this object. What you're seeing here is essentially this active galaxy that is where you're seeing, where you're seeing rotation, sort of that's the matter accreting on this supermassive black hole. It's a tiny black dot at the center. And then it's being ejected in this jet, which is this line. And we are looking right into the jet. And that's why this object looks so bright. Okay, so since then we have done other things. So that was from 2017. We have in 2020 we had we had roughly 10 years of IceCube data. We have done our sky map. So we have millions of events, and we have stacked them on top of each other. And we were looking for some directions that for which you would see more than average number of neutrinos. And there's one direction that stands out, and you're seeing it here in this sky map. It's coincides with the galaxy NGC 1068. And if you want to know, what does it mean to stand out, you see at the bottom right, you're seeing the graph. So the graph shows you the number of neutrinos we've seen as a function of the distance between the neutrino and that source. And you're seeing that the histogram actually, it peaks just at the source. And that is pretty significant. So that's what we call more than 4 sigma. So we are seeing more than 100 neutrinos just from this one direction. Now, what is this for an object? That's, again, an active galaxy. So I've talked about active galaxies before. Remember the ingredients that are needed: a supermassive black hole plus matter that falls onto it, that accretes onto it. In this case, you don't see the jet. There is no pronounced jet. And we're not looking into the jet. So we're seeing this galaxy a little bit from the side. Yeah, it's a beautiful spiral galaxy. Also, I mean, it's not just an active galaxy, but it's also a spiral galaxy. And we're seeing it a little bit from the side. It's one of the absolute closest active galaxies. So it's at 14 megaparsec. That's an astronomical unit. I don't need to explain it. And it's apparently a very strong neutrino emitter. It's very interesting for us because it actually shines very bright in neutrinos, as I said, but it does not shine bright in gamma rays. So apparently this is one of the sources where neutrino emission tells us about the inner mechanisms, acceleration mechanisms of particles, and no other radiation can inform us about what's going on but neutrinos. All right, this was just the second source. We have now, since then, even observed our own galaxy, and that's, I think, a beautiful result. It's 2 years old. So what you're seeing at the top is the radio emission. It's of our, the galaxy observed in radio. What you're seeing below is the optical emission. I spoke about the two. What you're seeing then below is the gamma ray emission. And remember in the introduction, I spoke about microwave, optical, and gamma rays. And so you're seeing essentially the same images again, but now just focused on the galactic plane. And what we have now for the first time seen is neutrino emission, also from the galactic plane. And the energy of this emission is of the order of 10 to the 15 electron volts. So it's extremely energetic, much more energetic than anything that you're seeing above. So very interesting for us. And, we are still trying to digest what this means. All right, with this, I conclude actually. So I have just as an outlook, we are doing this only since maybe 15 years. We are still accumulating statistics. I mean, neutrino astronomy is much older than 15 years, but IceCube has been operating since about 15 years. And IceCube is really far more sensitive than any other previous detector. And so it feels like we are still at the beginning. We are seeing very interesting things. I've only focused on high energy astrophysics. I have not focused on neutrino oscillations or anything else. And yet it's already quite interesting. The exciting thing is that we are just starting. So we are actually planning detectors that are 10 to even 100 times larger than what we are, what we have been discussing today. And so the big question is, what will be discovered next? Okay, thank you.
Thank you, Marek, for your exciting talk, and I would really like to thank you to make it accessible to the students. Now the floor is open for some questions. So if you have any questions to Professor Marek, then you can raise your hand. So he mentioned that what are the discoveries we have made using IceCube. So not only we have seen high energy astrophysical neutrinos, but now we know about their mother sources, right? So you have any questions, then you can come forward. Yeah, come. So you can introduce and quickly ask your question. Use the microphone.
Good morning, sir. Sir, I am Kapil Kumar, sir. And my question is that, sir, compared to other images, I think that the resolution of the image of the galaxy for the neutrino is relatively less. So, sir, I would like to know that why does it that happen?
Yeah, that's an excellent observation. Let's see, where do I have it?
You want to share the slide again, maybe?
Yeah, I'll show you the slide again. I just need to make sure I'm okay. So yeah, so it's
he's asking about the neutrino
yes.
row.
Yeah. So this is the resolution here is not better than 5 degrees. The reason why it's so poor is because we're using machine learning algorithms to reconstruct events that are not long tracks going through the detector, but cascades, which are almost spherical. And they don't come with a very good resolution. Now we are focusing on those events because they are starting the detector. These neutrinos are actually traveling down. So in Christian before, he explained how we differentiate between neutrinos and atmospheric backgrounds. And one way to do it is by simply asking, is the neutrino coming up or is it going down? If it's coming up, it's for sure a neutrino. If it's going down, then we have lots of more background and we can't know for sure. Now, for a certain class of events that are downgoing, we can still be certain that these are neutrinos, even neutrinos of cosmic origin. And these neutrinos are used to study the galactic plane because we need to, we're at the South Pole, so the galaxy in a sense is above us. And so as a result, we need to use these events. Now, these events, they don't come with good angular resolution, and we're using machine learning to produce the best resolution we can find, and it's about 5 degrees. And as a result, 5 degrees is not great. The disk is only 1 or 2 degrees wide. So that's why in gamma rays, it looks pretty fine, while in our case, it's pretty smeared out.
One may add that there are 2 detectors at the northern hemisphere, one in Lake Baikal in Siberia and the other in the Mediterranean Sea. And they look through the Earth to the galactic plane. They are just under construction, but when they are ready, they will have a better angular resolution because they can use these long tracks which are due to muons which come from neutrinos which have crossed the Earth. So with respect to the galaxy, these detectors are at better places than IceCube, our own galaxy.
So you understood that? So you are looking to our own galaxy, right? So from IceCube location, it is on the top. So you need to rely on the events which are coming from the top. For that, the angular resolution is 5 degrees, what Professor Marek told you. But he's mentioning about other two detectors when they will be ready. Then, based on their location, you will see the neutrinos from our galactic plane which are coming through the Earth. So then we expect that the resolution will be better. Okay. There are other questions. Yeah, come forward and you can ask. Be loud. Okay. Yeah.
Sir, good afternoon, sir. My name is Brijesh Pulkes. Sir, as you mentioned about the cosmic rays, so can you tell me some more things about the gamma rays burst?
About gamma ray burst, well, I can tell you a lot of things, but not sure what you're mostly interested in. So I've mentioned supernovae, and as a result of the collapse of the star, essentially, and having a very dense inner core where where matter falls bounces off, as a result you get a supernova explosion. You can have, under certain circumstances, if you have very fast rotating, very massive stars, you can have even more exciting phenomena, and that includes gamma ray bursts. So a supernova can, in a sense, explode in slow motion, but it can also produce these super energetic jets that I've already introduced in the context of blazars. You can have those jets also in the case of supernovae, in which case, if you happen to look into the jet, you will see a gamma ray burst. Now, the gamma ray burst might accelerate particles to higher energies, but we don't know. And so one of the things we're doing is we're actually looking for this kind of radiation, but so far we have not seen any.
Yeah, he has one more question. Yeah, go ahead, please.
Sir, also can you tell me more things about the Chandrasekhar limit?
The Chandrasekhar mass limit, yeah, that's a very interesting limit. Of course, Chandrasekhar is really a hero, among astronomers. So I definitely recommend to learn about Chandrasekhar, and in particular, of course, Chandrasekhar Mars. But he has done many things that are great. So Chandrasekhar Mars it's connected to white dwarfs. And when if a star stops essentially maintaining its gas phase through radiation, through burning, fusion, it will collapse, or it will contract. It will contract if it's to the white dwarf phase, where it's the electron degeneracy that will produce the pressure, and the pressure then stops. These white dwarfs they're much smaller than a star, and they can become hot, but they, in a sense, are radiating much less than a regular star because they're much smaller. So they are kept stable through a different mechanism. Now, a white dwarf is not going to be stable if it becomes very massive. There's a transition. So up to 1.4 solar masses, a white dwarf can be stable. But what happens if you push it further, and that's the Chandrasekhar mass limit, is that it becomes unstable, and it will then further collapse to a neutron star or to a black hole. Because it's just how the pressure is being produced. You transition from a non-relativistic to relativistic speeds, and so there's a transition and it becomes unstable. So you can produce these white dwarfs up to 1.4 solar masses, or up to the Chandrasekhar mass, but not beyond.
Yeah. Any more questions for both the speakers? Like, you have any questions for Professor Christian or Professor Marek? Yeah, you have one. So quickly, because Marek has to leave. Yeah.
Yeah, unfortunately, I need to leave now. So
Yeah,
maybe.
okay, Marek. Thank you. Yeah, can you please share your slides so that we can share with them? Yeah.
I should send my slides to you?
Yeah, so that we can discuss with them. Yeah.
Okay. Well, I don't think I need to run now, but I try to share it a little bit later, okay?
Okay, great. Thank you, Marek. Thank you. Thank you.
Thank you for your attention, and thank you for the opportunity. It was great talking to you. Bye-bye.
Yeah, thank you, Marek. So you have question for Professor Spiering, Christian Spiering? Yeah. He's around. So can you ask your question? Yes. We have some time.
So basically, I have three questions.
Three questions. So come forward. Come. And go slow one by one and raise your voice so that you
Okay,
can hear.
so my first question is that what neutrino data you collected from laser TX0506 apart from gamma rays?
What did you say?
What neutrino data you collected from laser TXS0506 apart from gamma rays?
Oh, so Christian, she's asking about TXS 0506, that event basically. Hello, can you hear, Christian?
Yeah, I did not understand the question.
So she has a query about that TXS event, TXS 0506.
Yeah, about TXS.
Yeah, that event.
And what is the question?
So you want to know about the event, right?
Yes, sir.
Okay.
Yeah.
So
What kind of force involved?
that is, by the way, the story is very interesting. Marek told you that that we observed this one event from TXS, which had a very high energy. So we sent an alarm to astronomers. And then the astronomers looked into that direction. And they found that this object is an active state. So in X-rays, in gamma rays, high energy gamma rays, in radio, it shows an excess of activity. So that was rather interesting, but by itself, it was not yet very convincing because it could have been an accidentally. Yeah, sometimes it happens that you see in high energy neutrinos and this object is an active state, but one neutrino is no neutrinos, so to say. Well, what we did then, we looked back to our own data and looked back to all the years of this object, all the 12 years, sorry, at that time it have been 7 years of data, and we saw that this object had already an excess over some months a few years earlier. By itself, this excess was not significant. That's why we did not pay attention at that time. But now this excess some years earlier, plus the coincidence of this one event from us and the high states in other wavelengths, that was significant. And so it was the chance probability, so the probability that is only by accident, taken all together, was lower than 100,000. So it was, typically you say if this probability for being accidentally is smaller than 1 millionth, it is a clear discovery. It was not 1 millionth, but it was about 100,000. So that means it was very clear, very close to a real discovery. So we did not call it discovery, but we call it convincing evidence. That is what we called it. But most people call it discovery. So that is the story of TXS. And TXS, by the way, is very far away. It is 4 billions of light years, 4 billions of light years. The other source, which Marek showed, NGC 1068, it is only, how far is it away? Okay, you count it in millions of light years, so that was much closer, but the TXS was really 4 billions of light years.
So I hope you got it that, it was a classic example of multi-messenger astronomy, as Professor Christian mentioned. It was a flaring blazer, and then it got confirmed that from some direction neutrinos are coming. We saw one event, but from that same direction, photons, the gamma rays, were also coming, and it was observed by other detectors. So we confirmed that, because you have seen today in the morning that from the same process, a cosmic ray can come, a neutrino can come and also the photons can come, right? So when you get confirmation from all these 2 or 3, it's a multi-messenger connection. So you have any more questions, or you have one more? So let's get one more. Okay. Yeah.
Okay, sir. How do you handle missing data in your neutron analysis?
What data?
How do you handle missing data in your neutrinos analysis?
Oh, so I think that question is, how do you handle your missing data in your analysis?
How do I handle missing data? What
do you mean by missing data? Like,
I mean, if you do an experiment on that, you just forget that, or there is a small neutron, you couldn't observe that.
okay.
Very small data that you couldn't observe.
Means
that.
you have not seen anything.
Yes, sir.
So if you have not seen anything, how will you do any analysis of it?
I mean that that is very small that you don't observe it very precisely.
Okay. So I'm not sure, but she's talking about some data which are not very precise. So do we take them in analysis basically or no? This is
yeah. Okay. What means not very precise? I mean, we precision in the sense of angular accuracy. That is, of course, very important if we want to identify individual sources. Because the better your angle, so our angular resolution is about half a degree. Half a degree is the diameter of the sun or the diameter of the moon, if you look to the sky. So to give you an example, that is of course much worse than the angular accuracy of optical astronomers or of radio astronomers. They are 1,000 times better than us. So our main point, our main idea is we want to build a bigger detector, which is IceCube Generation 2. And this detector will have 5 times better angular resolution. That means the background in this interval where we search is 5 times 5, that means 25 times smaller. So we have much better sensitivities to small excesses. And so it is also the case for these experiment in the Mediterranean Sea in water. They have also a better angular resolution, which is due to an interesting effect. Light in water travels rather straight and is not scattered much. So they can reconstruct the front of the Cherenkov light very precisely. We in ice have smaller absorption, which is good. Our photons from Cherenkov light, they live longer. But these photons are scattered because ice is not as such homogeneous as water is. And that means our Cherenkov front is a little bit blurred. And that means our angular resolution is worse than in water. So these water detectors in the Mediterranean, which are now under construction, but in 3 or 4 years, they will have also a cubic kilometer, they will have much better sensitivity to individual sources than we have. And in particular, as I said already, they have a much better sensitivity to sources in the galactic plane. So I do not know what you did. So then, of course, we look for excesses, and we see a lot of small excesses. We see excesses not only for TXS and for NGP 1068 that have been the 2 sources which have been discussed. We see also other excesses, but they are all not yet significant. If we take more data, they may become significant due to higher statistics. They may also become significant if we further improve our angular resolution. I mean, that's a lot of mathematics and art of reconstruction. So you can be sure that in the next 5-6 years, we will see other sources, but they are still not significant. The excesses which we see at the places where these sources are, they are not yet significant. I do not know whether this answers your question.
So you understood, like
Yes, sir.
we mentioned in the morning, the detector KM3 net
Yes, sir.
on the board. So that is a detector which is under construction in the Mediterranean Sea. So we have also gone into the ocean, and he mentioned that the water is much better than ice because there are no cracks or there are no structures. So when the photon propagates, so it will not be like a zigzag motion inside water, but in ice there can be multiple scattering. So you will have better angular resolution because you want to know the source, right? So you need to know have better angular resolution. So the missing information in IceCube, those can be discovered or precisely measured in this ocean detector in KM3 net. This is what he's mentioning. So if we miss something today, this is because of the lack of information in our setup. But we have hope that in coming days we will improve with a bigger detector, better detector, and this missing information will not be any more missing. Okay. So I think
Maybe,
we have some questions. Yeah,
maybe,
Christian.
maybe I add the following. We have in the moment the biggest detector very clearly is IceCube. So we have seen these sources, we have seen an excess at highest energy, which comes diffuse in our detector from all directions. But soon we will have this Mediterranean detector. We have already 0.5 cubic kilometer in Lake Baikal in Siberia. This is this Russian experiment. But now we have new players in the field. There is one detector under so to say, in prototype testing, which will be in the Pacific Ocean close to Canada. And another one will be built, presumably will be built in the South Chinese Ocean. And the Chinese people, if they start something, they do it rather fast and they do it rather big. And their plan is to build a 10 to 30 cubic kilometer detector, so 10 to 30 times bigger than ours, than IceCube. Of course, that will not happen in the next 2 or 3 years, but in the next 10 years, it could be possible. And then we have a network of cubic kilometer detectors or 10 cubic kilometer detectors around the world. And that's, of course, a fantastic thing. You can do a lot of nice gains. For instance, if a supernova explodes, then it emits neutrinos. And these neutrinos are emitted within 10 seconds. Such a supernova has exploded very close to our own galaxy, only 160,000 light years far from us, in 1987. And that was a big discovery all over the world. About 24, that means 24 neutrinos have been discovered. And there was even a Nobel Prize for that to the Japanese Super Kamiokande experiment. Now, if such supernova would happen today and it would happen in our own galaxy, we would see it in all these neutrino detectors. And then we could calculate from the arrival time of these pulses, short pulse of neutrinos, we could calculate the direction from where the neutrinos have been emitted. We call that triangulation. So if the neutrinos here come earliest and the neutrinos there come later, then I know this front comes more from here than from there. And if I have 5 or 10 detectors on the Earth which see these neutrino pulses, we can make a triangulation with an accuracy of better than 5 degrees. So since these neutrino pulse comes earlier than the light pulse comes hours later, 1, 2, 3, 4 hours later. That depends on the on the size of the supernova, on the mass of the supernova. So we see the neutrino pulse, and we know the direction, and we can tell the astronomers, okay, dear astronomers, in a few hours, there will be a supernova, and it will be in that direction. Take your optical telescopes and look into that direction. And then they can see exactly the moment when this new supernova appears optically, and they can study the initial phase of the optical pulse, which was not possible for the supernova in 1987. So neutrino detectors are really a fantastic early warning system for the astronomers. And that's again what Sandeep called multi-messenger astronomy. So we alone are not very useful. We are mostly useful, of course, if we work together with radio astronomers, optical astronomers, and gamma astronomers.
So you heard, like, we are hearing IceCube throughout the day, and you heard sometimes this ocean detector, right, KM3net, which is now under construction. He mentioned there will be 2 more detectors in the next 10 years. One is in Canada, it's called P1, and another in China, in South China Sea, is called Trident. And if Chinese will have proposed something, they are very fast. And their detector can be 10 times or even 30 times bigger than IceCube. So when you will be around after your PhD or something, there will be full network of these detectors in China, in Canada, in South Pole, in Mediterranean Sea. And you have a global network of neutrino observatories. You understand? So what he's saying, when you have global network at various places, then your prospects will be much higher. Suppose if there is a supernova explosion, if any explosion happens, neutrinos will be the first to reach you. So one of these detectors will see that, right, and see their location. And then they will tell the astronomers that, look, I have seen the neutrinos from that direction. After a few hours, you will see the photon. So why don't you turn your telescope there, basically? So this is the multi-messenger astronomy. So you should be very happy that there are more detectors coming, because this is just a beginning of this field. So thank you, Christian, for sharing this, because we didn't discuss about P1 and this Trident, but looks promising. They look very promising. And this is very good for the community to have more experiments. So I think we had some question answer session, and we should thank again Professor Christian Spiering. So thank you, Christian. And I must say that your talk was fantastic. You know, at the right level, we enjoyed. In fact, I learned a lot, and I hope that we will be able to talk again, you know, and we can learn from you. So thank you for being with us today.
Thank you all for you in India. Bye-bye.
Yeah, I think it is a lunchtime for you. So thank you, Christian. So now we should break for the tea, and tea is outside with some snack, and we should come back here at what time, Krishnamurthy? 5:20, right?
Yes.
So we should come back in 20 minutes at the same place. You remember you are doing something in your laptop? What did you do there that time? You differentiate between cascade, but then here's more surprises. You need to know low energy. Are you excited? Very good. So let's go have a break. Come back in 20 minutes. The highlight is at 6:15 when you talk to people from Antarctica. So be ready with your questions. Okay? So let's go outside.